Now we find ourselves on some cloudy ridge on Oahu, where we're going to talk about red-black tree insertion and deletion, the last in the series on balanced trees. So insertion in a red-black tree is almost exactly like insertion in a binary search tree, because these are a representation of binary search trees, except that we're always going to have these extra empty leaf nodes. So, for example, if we're going to insert 4 into this tree, we look at 6, we search for 4, so we go left, it's smaller, we go right, it's bigger. And in a binary search tree, we would then put the 4 right here where the Z node is. We do the same thing here, but we also have to add these empty leaf nodes, and that's, of course, what we have over here in this figure. And the inserted node is always colored red. So that is the first part of insertion, but now we have to check the red-black tree properties. So this insertion has preserved the color property that every node is either red or black because we colored our inserted node red. It's preserved the root property. We didn't touch the root node, it's still black. And it's preserved the external property because we added 2 black leaves. Every leaf is still black. And it preserves the depth property. We didn't add any black nodes, so if the depth property was true before, it's still going to be true that all the paths from the node to the descendant leaves have the same number of black nodes. Okay, but that leaves the internal property. If a node is red, then both of its children are black. So if the parent of the node we added, the parent V in this diagram of the node we added Z, is black, we're done. The internal property is also preserved. But if the parent is red, we have a double red, as shown in this diagram here, a violation of the internal property. Before I go on to how we do that reorganization, I want to diagram these as 2-4 trees so you can see what's going on in that representation. So let's look at what these red-black trees are in terms of 2-4 trees. 6 is black, so that's the basis of a node. Its 2 children are red. That means they are part of 6's node. So essentially what we have here is a red-black tree that looks like this. A 2-4 tree that looks like this. 3, 6, 8. It's a 4 node because it has 3 keys and 4 children. Okay. And then when we did the insertion here, we added another red node. So what happened here? Well, 6, there's only one real node in the 2-4 tree because there's only one black node here. But then there's 3 other members of it. So we essentially have the smallest one is 3, since 4 is bigger than 3 and smaller than 6. 3, 4, 6, 8. So this is actually a 5 node, which is not allowed, and so that's why we have to fix it. So you can see that this internal property violation, that means we've jammed one too many keys into the node in the corresponding conceptual 2-4 tree. So even though this is a legal binary tree and it's even a legal binary search tree, it's not a legal 2-4 tree. So let's see how we can fix this thing here to be a legal 2-4 tree. Now here I'm returning to a previous screen. You may remember that with 2-4 trees on a previous screencast, overflow in 2-4 tree representations were handled with a split operation where we took the node that had too many keys in it and we split it up into 2 nodes here. It turns out that the situation we're looking at now with red-black trees could be this situation, but it could also be simply an incorrect representation of a 2-4 tree. So here we are back in the red-black world, but with the 2-4 trees corresponding to them next to them. So the case we saw previously was the overflow case, which is where you have a 2-4 tree with too many keys, and this is an example of the red-black tree situation where you've got a double red, which means we've jammed too many keys in here. So that's the one we've encountered before, and we're going to deal with that by doing something called recoloring, which is super simple. We just change the color of the nodes. We don't have to do any restructuring. But there's also the possibility, case 1, that you have a double red from what's an incorrect representation of a 4 node. So that's where we have this situation, the correct number of keys, but incorrect representation in the red-black world. So we're going to look at how to fix both of these things. So case 1 is the case where we have the incorrect representation of a 2,4 tree. So in the 2,4 tree in this restructuring operation, the fix-it is not going to change. The problem is that this does not correctly represent the 2,4 node, because with this 2,4 node here, the 6 is supposed to be the black node, and the 4 and the 7 are supposed to be the two red children, as we have over here. So what we do basically in this kind of situation is we do a rotation. Remember in the previous screencast I mentioned that there's rotations that maintain the binary search tree properties of the parents being bigger than the left child and smaller than the right children, while fixing 2,4 tree properties that are expressed in the red-black tree properties. So here we have a situation where we have 3 keys, 4, 6, and 7. 6 is the middle key, so it obviously belongs up at the root here. So we do this rotation where 6 gets rotated up and becomes a parent of 4 and 7, like we did here. So now we have just the same number of red links, but they are now a correct representation of the 2,4 node, where the 6 node is collecting together its sibling keys in the 2,4 representation of 4 and 7. There are actually 4 of these configurations requiring restructuring. All 4 of these are incorrect representations of what we really want down here, which is this 2,4 tree node. But in all 4 cases we have double reds in different configurations. So in each of them you find the middle node, the one with the middle value, which is the 4 in this example, and you bring it up to be the black node and make it the parent of the other 2 nodes. So this fact that there's these different cases leads to the complexity of the code in red-black trees. In insertion and also deletion we'll have different cases. We're not looking at the code in this screencast. That would make it way too long. You should read the code in the Cormen textbook and understand how it's handling these cases. But after this restructuring, we've remedied the double red. We now have only single reds, and we haven't violated any other properties because we haven't changed the color of the root node or the child nodes. We haven't changed the number of black nodes in the tree, so the number of black nodes on the way from the root to the children are going to be the same. Okay, while restructuring was resolving the problem, the situation where the sibling was black, and it was just an incorrect representation, recoloring will be remedying a situation where there's overflow, the one we saw also in the 2,4 representation. So this is where the parent red node has a red sibling. So we've got a double red, and the parent red node in that double red situation has a red sibling. And so that means we're packing too many nodes into a 2,4 node. It's really a 5 node. But the fix is really simple, at least locally. We just notice the structure here doesn't change. We just change the colors. We just change the color of the root node of this subtree to red, these 2 to black, and we leave that one alone. So we're just flipping the bits on these 3 things, and that does this transformation where now this 4 node is now up somewhere else, possibly with some other keys, and the part of the rest of the tree we've dealt with, we made 2 become its own root node, and 7 became its own root node with the 6 in the subtree that corresponds to having 6 in its 3 node here. So we're splitting a 5 node into a 2 node, a 3 node, and sending a key up that you may remember we talked about earlier. Of course, notice that since this node has changed color, that means it's gone up to become a member of some other higher level node in the 2,4 representation. It's possible that this will then cause overflow in this higher level node, which would correspond to the double red being propagated up, because we just turned a node here from black to red, and that may violate, if its parent was red, then you have a double red up here, and so that will require the log n propagation up the tree to fix that. Just a few comments to finish up the insertion. As we've already mentioned here, the double red violation may propagate up. The time complexity of insertion in 2,4 trees is theta of log n, and we can get the same result here, basically relying on the fact that the red-black tree is no more than twice as high as the corresponding 2,4 tree. But we can also note that in the red-black tree we're going to search down no more than the height of the tree. It is a balanced tree, and the adding items are order of 1. and restructurings, recolorings, and restructures also constant time, and then we have to do at most log n recolorings on the way up, and one restructuring. Each restructuring finishes fixing the problem, so that doesn't propagate up. So insertion is theta of log n in the red-black tree representation. And as before, it's possible to do a top-down version of this where we restructure on the way down, so you don't have to do a second pass up the tree, and that's the approach that the Sedgwick textbook takes. For deletion, let's first recap the 2-4 tree deletion. Remember that we, like in binary search trees, we would find the successor of a node and move it up there, replacing that node that goes up there. And so we only need to be concerned with what happens at the leaf 2-4 tree node here. And as explained in the last screencast, we had the possibility of underflow, where you get too few keys in a leaf node. And in one case, if the sibling only has one key here, we just merge them together, and we have to pull down a key for that merger. That goes to this node here. Whereas if the sibling has two keys, we kind of rotate the keys around like this. So we move the 8 up, the 9 down, and that fills this node here. So now we're going to look at the corresponding operation in the red-black tree. So in the red-black tree world, essentially you begin performing deletion just by doing the BST deletion. That, of course, involves an internal and an external node, because we replace a node with its successor in the binary search tree. So we can preserve the red-black tree properties by just giving that successor the same color of the node deleted. When we move the successor up into the binary search tree higher up, we can just give it the same color. So within the tree, we don't have to worry about violation of the red-black tree properties. We have to look at possible violations at the bottom of the tree. So here's an example where we're going to delete node 8, which is V, either because we're deleting it directly or it's the successor of a higher level node that was going to be deleted. And so when we remove 8 from the tree, we're going to just replace it with its left child R. But we have to pay attention to the color. If one of these two nodes is black, we can just color this new node here black, and we're okay because we haven't changed the number of black nodes on the path between root node and these leaves. But if both of these nodes were black, then we have merged together two black nodes. So by having only one node, we've changed the number of black links on the way to the path. And we mark that with this fictional color called double black, which indicates that we now have two blacks packed into this thing here. And so a double black is something to be fixed, and it corresponds to an underflow in 2-4 trees. So here's the underflow as represented in the 2-4 representation. Essentially, it's saying we don't have enough keys to make a node here. That's what this thing in the red-black tree representation means. And we've seen this situation before with underflow, that if there was just a sibling has just one key over here, we would merge them. If it has two keys over here, as in this situation, we're going to shift the 4 up and the 6 down in the red-black, in the 2-4 representation. This is the 2-4 representation. So we have to ask, how does that happen in the red-black representation? So this is where deletion gets complex. It has 3 cases in this presentation by Goodrich and Tomasia. And it depends on the color of the sibling. So if the sibling Y of the node that's got the double black, which is R, is itself black and has a red child, that corresponds to, so here's 2 keys, 3 and 4. Those 2 keys are together in this node here. And we're going to do the transfer of keys I mentioned earlier. The 4 is going to go up, the 6 is going to go down, and giving this result here. But in the red-black tree, that corresponds to doing a rotation, where this 4, which is down here, has to go up and become the root node here of this subtree with 3 and 6 as its children. And they all become black because they're all 2 nodes. They all have a single key. So the second case is when Y is black and its children are both black. And so this corresponds to the Y node having just one key with 2 children. And we have our underflow, the double black in the red-black tree representation corresponds to an underflow in the 2,4 representation. And as before, we needed to merge these two nodes together into one. And so in the tree representation, that can be, in the red-black tree representation, that can be done with just a recoloring, because having a black node with a black child indicates that these are two separate nodes. If we just color the child red, we now essentially are merging this key into that node in the 2,4 representation, and we get this. So this is equivalent to a 2,4 fusion in the 2,4 tree representation. It's possible for the fusion to propagate up the double black violation. So we dealt with where Y is black and it has a red child, and where is black and it has black children. But now what about where Y is red? This is Y right here. So this is a situation where we're going to transform it into another red-black tree that one of the other cases will apply to. This lets us reduce the number of special cases that we have to write code for. Both of these trees will correspond to this red-black tree down here. So we have a 6 with a child of 3 that's red, so the 3 and the 6 are together, and then those children are both black, so they are in their own nodes here. And here we're going to transform it with another structural transformation, a rotation, but here we're going to bring the 3 up to be the root of this subtree. That requires moving the 4 over to be the left child of 6. Again, you should always verify we're maintaining the binary search tree properties. All the keys in the left side are smaller than 3. All the keys in the right side are still larger than 3, even though we changed what node is the root of this tree. So it's still a BST, but and also this here we have a 3 and a 6 rather than the 6 was the dominant node here, and the 3 is the red child. Here is the 3 is the dominant node, and the 6 is the red child. But both of those correspond to this node in the 2,4 representation. So we actually have not changed the 2,4 tree by doing this manipulation, and the 2,4 tree is still not legal because remember it has to be fully balanced. This is an underflow. There has to be a key here. So we still have to fix something, but we've now transformed it into a case where the double black node has a sibling to which we're going to be able to apply one of the other cases, because the sibling here is now black, not red. We're no longer in the Y is red situation. So you should look at how those cases are all mapped to the code in the Cormen et al. Textbook. It's tedious. These are one of the most tedious data structures for modifying, but it works so well that the Cormen implementation of red-black trees, the Cormen design of the algorithms for red-black trees, is what's used as the Java tree implementation. And finally, we'll just note briefly that the time complexity, as we expected, is theta of log n, because we have to search, we have to pay that cost to find the deletion point, which may be an internal node, but we always have to search to find its successor at the bottom of the tree. And then we're going to have constant time restructuring operations, but we may have to propagate them up, yet that is also bounded by log n, so the overall deletion is log n. Let's note that these are not the only kinds of balanced trees. One of the first ones invented was are called AVL trees after the initials of their authors, and it also maintains a balanced tree by requiring that the heights of the left and the right subtree differ at most by 1. You have to use some extra storage to record the height differences. They've got log n operations like red-black trees, but they may require log n rotations to rebalance, whereas the red-black tree can, in some situations, rebalance without that log n cost. B trees are a form of those multi-way trees, where they're used often with disk storage. You can have very, very high branching in a B tree, many, many, many children, but a fixed number of children. And the B trees are designed so that reading in, this of course would correspond to a giant node that has, key data, key data, key data, key data, key data. And they're designed so that the size of this node corresponds to what you do in one read of a sector of a disk, because the greatest amount of time in reading from a disk is moving the head and then waiting for the disk to spin into position. After you've paid that cost, you want to read in as much data as possible. So you design the node of a tree to fit exactly that read, and so you get as much into primary memory, RAM memory as possible to speed things up. And then we have splay trees, which are also binary trees, but they operate very differently. Rather than having rules about properties to maintain and not having any extra labels required on the nodes, it just does these operations as you access the tree. It does these restructuring operations every single time you search for something. And if you search for a node often in a splay tree, that node will move up towards the root, and so it'll be accessed faster. And we're going to study that one later in the semester. And finally, I just want to point out that in the web notes here, there's a table relating the 2-4 tree action to the red-black tree action and what they do. It's done for both insertion and deletion. And also there's a table here that compares the various dictionary representations that we've been working with here. So you may want to look at that as a nice summary of their relative properties. So that concludes our overview of red-black tree insertion and deletion and the series of screencasts on balanced trees, here being balanced somewhere on a ridge above Manoa Valley.